So yesterday, we started off with talking about how the nucleus could change and where it got all the energy. And now we're looking at the specific kinds of particles, and we looked at one of them yesterday. The first one in the alphabet, well, at least the Greek alphabet, the alpha particle. So, and we said that an alpha particle is a helium-4 nucleus. Okay. And it's got to have a positive charge because it's got 2 protons, 2 neutrons. So it's got a positive charge. The protons make it positive. Of all the particles that come out, it's the most massive. Got the biggest mass of the particles that are coming out. And because it's got a charge and it's massive, it interacts with atoms along the way. If it didn't have a charge, that wouldn't have worked for Rutherford. Rutherford's experiment wouldn't work unless this had a positive charge. And if it wasn't very massive, it wouldn't be able to get close to the nucleus. It had to be heavy, okay? Because it's got to be hard to turn. I mean, when you did that, the simulation of Rutherford's experiment, and I asked you what angle you had to get so it was going to bounce, how close you had to get to the thing before it was going to bounce back, the answer worked out to be about 0.35 femtometers. And it was letting you do hundreds of femtometers. But you had to get within 0.35 before it went more than 90 degrees. Okay? It's hard to turn. It's got to get really close to the nucleus before it turns. If it was light, it would turn easily. Okay? So, looking at the math, look at the numbers. Remember that the numbers up top always have to add up on both sides. So this 210 has to equal that 4 and that 206. That's how these equations work. Okay? And the bottom has to add up too. That the 84 equals 82 plus 2. The top numbers equal each other, bottom numbers equal each other. That was the last question on the reading guide, if you missed it. That's why that's what they're looking for. Okay? But every time I make one of these, the same thing is going to happen to the mass number. And the same thing is going to happen to the atomic number. Every time I make one of those, that atomic number has to go down by 2. Right? And the mass number's got to go down by 4. Now they're trying to horn in on our action. Okay. Every time, those numbers have to change the same way. Now, usually you get alpha particles when you got big pieces, okay? So that you can afford to lose a big, you're not going to find an alpha particle coming out of something that's only got 6 protons. Okay. So the first one discovered, alpha particles. Second one discovered was, second letter of the alphabet, in Greek, beta. Okay. Yeah, I'm going to have to say something. Sorry, guys. That'd be great. They put the horn section outside my door. I don't know. It's probably not a good idea. Okay, so this is a beta particle. Hey, a beta particle is an electron ejected from the nucleus. What's the obvious problem with that sentence? There aren't any electrons in the nucleus, but there's an electron that comes out of the nucleus. Okay. Now we said that we wanted a 1-to-1 ratio if it was going to be stable. If you're down below 20, So since this is number 6, it should be pretty close to 1 to 1. But it's got 6 protons and 8 neutrons. That's not 1 to 1. Right? It's got too many neutrons. We see that carbon-14 has too many neutrons there. We can tell on this one because we know it's supposed to be 1 to 1. Okay. So got too many neutrons. So a neutron gives up an electron and becomes a proton. Okay, so told you we weren't going into this, just going to mention that they're there, that protons and neutrons are made up of smaller pieces called quarks. The quarks that make up a neutron can be separated into a proton and an electron. As long as so what would happen would be the weak nuclear force here is the one that's happening because it's happening inside the neutron. Inside the neutron and proton is weak nuclear force. From proton to proton is strong nuclear force. Okay. So you get an electron, okay? Okay, so E for electron, 0 because the number of protons plus the number of neutrons is 0. -1, why is that there? To make the math work. Does that make sense? You need to make the math work. So they label it that way just so the math works. Okay? So every time I do this, the atomic number has got to change, and it's going to change by going up 1. And the mass number is going to stay unchanged. So carbon-14 turns into nitrogen-14. Now, we wrote this because it's an electron. We could have also said that it was a beta particle. And the Greek letter beta looks like a bee with the tail down here. It's a beta. So I could have also have written this with the same numbers for beta. Alpha? Oh, alpha looks like a sideways fish. That's alpha. Okay. A V that people got in a hurry with. A V that people got in a hurry with and made a loop. Okay. Positron emission. Okay, it ends in ON or TRON, like electron and neutron. So it's talking about a particle. Okay, and what do you think the name gives you a clue about what its charge is? Positive. Okay, so a positron is the same mass as an electron, but with a positive charge. Well, how come I never see positrons? How come they never told me that? Where are the positrons in the atom? Okay, positrons fit into a different category than matter. Okay, our universe is built up of everything where positive pieces are positive and negative pieces are negative. But you can build an entirely different universe if the charges are reversed. And that's not called matter, that's called antimatter. Okay? So there's an antiproton. Same mass as a proton, but the opposite charge. Does that make sense? Okay. Now, when matter runs into matter, or antimatter, they annihilate each other. And annihilate means completely destroy. So the mass of both pieces goes away. And when the mass of both pieces goes away, you get a lot of energy. Okay? You don't want to be around where matter runs into antimatter. Now, we can't store antimatter very well, because what are you going to store it in? Because if it touches the thing, it's going to annihilate. So, but how do you store that antimatter? Oh, just make the whole universe out of antimatter, and you'd be okay. Except you'd be made out of matter, and you'd blow up. But it happens when you slam pieces together. Those quarks that make matter, if you put them together differently, make antimatter. Dark matter, they don't know. That's why it's called dark. Because what is they calculated how fast the galaxies should be expanding away from Earth, and they're not expanding fast enough. There's got to be some more mass to slow them down. There's some mass slowing them down. They don't know why. Okay? So dark matter, matter we can't see, but they're not sure what it is. Okay. Okay, so a positron is antimatter. You're never going to run into them except in, sometimes they do it on purpose. If you get a PET scan, P-E-T, you heard a CAT scan. We'll talk about CAT scans and PET scans and MRIs along the way. But PET scans, what they do is it's called positron emission tomography. Tomography means to map. Positron emission, so they give a source that gives off positrons and they shoot it at your body. When it hits an electron in your body, it annihilates and sends off that energy and lets you know where it was. So they can map where the electrons are at in your body, which means they can map everything in your body. Does that make sense? Yeah. So this is what the equation looks like. Okay, so it's 1 to 1, but it's right close to 20. So at 20, it's a gradual increase. So we're trying to keep it close, but if anything, it's going to be over 1 to 1 because it's really close to that 20. Okay. Okay, so what happened here? Well, let's look at the pieces. I had 19 protons. I got 18 protons. All right, so I decreased the protons. What about the neutrons? Well, here I had 19 neutrons. Here I have 20 neutrons. So I lost a proton and gained a neutron and a positron, which means that proton turned into a neutron and a positron. Does that make sense? Okay, so that means we're going to do this if they have too few neutrons, if your ratio is too small. So the proton gives up a positron and becomes a neutron. So if you look at what you have too much of, that's what's going to change. If you got too many protons, you're going to get a positive charge out, and you're going to make the positron. If you have too many neutrons, you're going to get the electron out. That's how that ratio tells you how it's going to change. What? Oh, it's bizarre stuff, and really thing is because all we can see is effects. We can't actually see the causes. It's all invisible to us. All we can do is try to see where it lands. Okay, so what's going to happen to my numbers every time? Well, what's going to happen to the atomic number? Well, if I got a +1 here, it's got to go down by 1 every time. And what happens to the mass number? Stays the same. I don't memorize any of this stuff down here. I write I put the stuff in the right spot of the equation and see what's going to happen to the numbers. It's not worth memorizing. But if you look and see what has to happen to the numbers, when you put the piece, as long as you know what the pieces are, you can always figure out what's going to happen to the numbers. Yeah. You have to know alpha, beta, gamma, positron. Yeah, and there'd be a few more decays we got along the way. But know the piece, and you know how they change. Does that make sense? So as long as I know the piece, I don't have to memorize how they change. Oh, no, the formulas? No, because you don't have to memorize them because you can always figure them out. In fact, that's what we're going to do today. We're going to figure them out. Okay, and I could also put that beta in. Ever see how I could have put the beta in? This is a positron because the beta doesn't have a 1 minus next to it. It's got a 1 plus. plus 1. So if it's plus 1 on the bottom, it's positron. If it's not, it's electron beta particle. Okay, so what's your homework going to look like? Oh, you'll need a periodic table. I can't do it without a periodic table. But I only need it at the very end. Because if you look at this, potassium 42 gives off a particle and makes something else. What is this something else? Well, do it by the numbers. What's the top number going to be on the other side? They got to add up. So what plus 0 gets you 42? Well, that would be 42. What's the bottom number going to be? What minus 1 equals number 20? And number 20 on the periodic table is calcium. Really, really hard? Integer addition and subtraction, folks. Here we go. Okay, what kind of decay is this? Identify the particle, you've identified the decay. Oops. That's a beta particle, so it's beta decay. Beta particle, if you get a beta particle, you did beta decay. It was beta. Identify the particle, tells you what kind of radiation you had. Yeah, you need to know the symbols because without the symbol, you need the numbers. But it's not a complicated list. Okay, so 226, what plus 4 makes 226? 222. What plus 2 equals 88? And number 86 on the periodic table is radon. Okay, what type of decay? What's that particle? That particle's an alpha particle, so that's alpha decay. Okay. I want the homework now. There's a couple other little pieces, but yeah, this is as hard as it gets. Oh, because it's going to have a plus on the bottom, so you're going to turn a proton into a neutron, not a neutron into a proton. Okay. Here's one of your artificial transmutations. Peter. Okay. Here's one of your artificial transmutations. They're putting pieces together, and then you make something different. Okay, so the top number adds up to 243. So over on this side, it's got to be 242. PU. Okay. Hey, what kind of decay is this? What's this? It's an alpha, so it's alpha decay. That's an alpha particle, so it's alpha decay. Bismuth, like in Pepto-Bismol. It's the biz in Pepto-Bismol. Bismuth. It's called Pepto-Bismol because it's got bismuth in it. Okay, now, let's make sure the stuff on the left-hand side of the arrow is the stuff you start with. Stuff on the right-hand side, because I'm going to give you some sentences that you have to translate. Decide which side it goes on. Read the sentence carefully. What you start with goes at the beginning. What you end up with, it goes on the right-hand side. Okay? Arrow does before and after. Okay, there's another change that's not a decay that they listed in there. Electron capture. Okay. What do you think happens in electron capture? And what's going to capture the electron? What part of its atom? What part of its nucleus? Which one's going to be attracted to the electron? Proton. So the proton's going to get hit by an electron and make a neutron. So if I shoot a high energy beam of electrons at silver 106, every once in a while an electron will break through and actually hit the protons in the nucleus. What will it make? Okay, well, what's the top number going to be? 106. What's the bottom number going to be? 46. So it's palladium. So a proton got hit by an electron, so I lost a proton. But the net mass number is the same, so that proton I lost must have turned into a neutron. Right? That's the way the top number stays the same, is if the proton turns into a neutron. Okay? So this happens when there's too few neutrons. That would make our neutron to proton ratio too small. And what's going to happen every time this happens? What's going to change? The atomic number is going to go down by 1. So this is the equivalent of a beta decay in the it has the same effect as a beta decay. Or as a positron emission. Has the same effect as positron emission. Your atomic number goes down 1. And then the other kind of radiation is gamma, but I didn't put it with the other one because gamma radiation is just energy. It's just energy. It's not a particle. So all the energy, that destroyed mass has to be turned, all of it gets turned into energy, and that energy comes flying out of the nucleus as gamma ray. Okay, this is the symbol for a gamma. It has 0 protons and 0 neutrons. Okay, notice this isn't a gamma decay. Notice I didn't put gamma decay, I put gamma radiation, because gamma radiation accompanies the other changes. So I did a beta decay, and along with the beta decay, I got some gamma radiation. Because when you annihilate the mass, or destroy mass, you got to get rid of the energy somehow. You can put it into a particle flying out fast, or you can put it into radiation, gamma radiation. Gamma radiation is very high energy. You don't want to be around it. But you won't complain for very long. Actually, it's a problem. Our sun is going through nuclear changes all the time, and it is shooting out gamma rays all the time, and alpha particles, and beta particles. Lots of high energy things are streaming out of the sun. The magnetic field around Earth protects us from it. It traps charged particles that absorb those pieces so they don't get to us. But if you want to go to Mars, you've got to leave the Earth's magnetic field. So one of the real problems with Mars is we don't think people can survive the trip there and back because they got to spend 6 to 8 months on the way there and 6 to 8 months on the way back. And once they leave Earth's magnetic field, Mars doesn't have one. And there's not one in between. So they're going to get pounded with gamma rays and particles all the way to Mars and back. How do you stop? 6 to 8 months, yeah. 6 to 8 months. So you spend a year being bombarded by gamma rays, you're probably going to have cancer. Okay. How do you treat cancer on Mars? You don't. So it's not about getting the rocket there. It's making it so we can survive the trip there and back because of radiation.
But if people have cancer, how can they treat cancer with radiation?
Because rather than shooting all over their whole body, they aim it at specific spots. When my mother got it, she had breast cancer, and they had like 6 lasers, and they all came from a different angle, but they all intersected in one spot. So the spot where they intersected got all the radiation along the way, got lesser radiation. So you're taking a chance along the way, but you need to kill the stuff you know is there. Yeah, when you're killing cancer, you got to kill yourself too a little bit. That's what chemotherapy does. Okay, it's not charged, doesn't change the atomic number or mass number. It's just a way of getting rid of energy. It's just a way of getting rid of energy. Okay, so I showed you the graph about the ratios. I've got that same graph, but I've got it in color where it tells you which way it changes. Okay, so color-coded, positrons are orange, betas are blue, alphas are yellow. We'll talk about nuclear fission and the other ones. They're way out extreme outliers. We're not going to run into those. So alpha, beta, and so look at orange, blue, and yellow on this graph. Okay, why don't you unzoom? Okay, so if you look, blue is up top, where you have a bigger number of neutrons than protons. Okay? The stable ones are the black ones. So things above the stable ones tend to go through beta decay because they have too many neutrons, so they turn a neutron into a proton. Okay? Things below the line tend to do positron emission because they have too many protons, not enough neutrons. So if you want to turn a proton into a neutron, you get rid of the positron, and your ratio is closer to what you want it to be, closer to a stable ratio. That make sense? Notice where alpha, all the way up here. You've got to be a really big atom before you start doing alpha decay. Yeah. Hey, and here's the really cute part. See all the stable isotopes? You will notice that there's not one right here. That right, I see if I can get a pen there, right here. Nope, sorry, it moved on me. Right there. There's no black dot. There is no black dot there. That element doesn't have a stable isotope. Well, if that's, so it turns out to be, it's pretty easy to find on the periodic table. Number 43. How can I tell? Because it's hollow on my table. Just outlines. It doesn't exist in nature. Because if you had any, it would have fallen apart by now. So, technetium, number 43. You'll see that it has a parentheses around its molar mass, its average mass. Okay, so we'll talk about half-life later. But for the rest of the day, we'll get you started on for me, oh, you should have. Should have two sides. Make sure you got two sides. Thank you. I'm coming. Thanks, Riley. Okay, before we get too far into this, because I've graded this assignment many times, and I know where the mistakes are going to be. Okay, read letter C on the bottom. Number 3, C. Which side of the arrow does Neptunium-233 go on? Right side. Of which one does Americium go on? Okay. Read D. Where does Neon-22 go? You see why I'm pointing that out. You got to decide which side they go on. That's the mistake you're going to make. Yeah, is formed versus turns into, or become. Or you start off with it and it goes through the decay. So if you start with it, it goes through the decay. They're on the left-hand side. If it's a product, it's on the right-hand side. And you can see how that mistake could happen.